Alright, there we go. Having some issues with my headset lately. Sorry about that. I had to get out the electrical contact cleaner and spray part of my headset because the right ear wasn't playing any sound. And not that I really need sound, but if I do for some reason, it's super like off-putting. It like makes me lose my balance and feel queasy and stuff. Anyway, that's working now. Welcome back to Chem 140. Today we're doing Unit 12, which is the return of calculations. So you're going to need a calculator, and you're going to need periodic table, the ptable.com. I almost said periodictable.com. That would be something different. For today's lecture, agenda items that are on the screen. Let's see. Quiz number 5 is due tonight. That is a soft deadline. That is a soft deadline, but make sure that you try and get it in tonight if you can, because quiz number 6 is due tomorrow, and that's also a soft deadline, but that will be the final call for quiz number 5. So you do have 2 quizzes coming up in a row. Make sure to stay on top of the material. Better to get those out of the way now than have them all pile up at the end of the quarter. What do we got going on here? We have, let's see here. Yeah, so the first part, we're definitely going to need ptable.com, so let's just type that in the chat here. There you go. So we're going to refer to that today because what we're going to do is we're going to calculate the masses of compounds in AMU. And in order to do that, you might want to use a different website, actually, now that I think about it. Which I'm going to paste here, and we'll get to what this is in just a second, but you can click on it if you'd like. All right, so for this first section, we learned how to calculate the atomic mass of elements in AMU. We did this long, drawn-out calculation doing weighted averages and stuff like that to get the average mass, which is the number reported on the periodic table that we use. Now, in units 12 and beyond, we're going to want to do this process for formulas. As in, like, what would water's atomic mass be? Well, it's not an atom, so it'd be molecular mass. What would its weight be? And the way that you do that is you just simply go to the periodic table and add up all the elements together in AMU and report the result to the correct number of Sig Figs. Yes, you do have to do it to the correct number of Sig Figs. However, there is a shortcut of sorts that I'm going to show you in a second, so you just don't have to worry about it since you're doing addition over and over and over again. So for instance, let's suppose that I wanted to figure out the formula mass of this compound, tin 2 fluoride. So what I do is I go look up what tin is, and that's this. And then I go look up what fluorine is. Now, I have 1 tin and 2 fluorines, so 19 times 2 is 38. And we'd report that to 4 Sig Figs. And then I'll just add these two together vertically. And there you go. Now, this gets super tedious, because as we go through the quarter, you're going to get bigger and bigger and bigger formulas. And really, this kind of just boils down to, oh, I have to add numbers again. Great. Yep, let's go look up phosphorus. All right, there's oxygen. How about chlorine and calcium? Okay, cool. And then the next problem, oh, I got to go look up calcium and then magnesium and then oxygen and silicon. And yeah, at some point we basically say, okay, you know how to do molar masses and formula masses. That's trivial. Like, for instance, okay, let's look up all of these things. Okay, well, nitrogen is 14.01 AMU. And I have 2 of them because of this right here. Hydrogen is 1.008 AMU. I got 4 of those because of this 2. And then carbon is 12.01. I only have 1 of those. And oxygen is 16. I have 1 of those. So now I gotta multiply this by 2. I gotta multiply this by 4. And then add all the results together and deal with sig figs and just, ugh. I don't want to. There's gotta be an easier way. And that's where Lentech comes in. I feel like I should have like some cheesy infomercial music playing whenever I show you Lentech. I don't know. What Lentech is it's technically a water treatment company, but they have a molecular weight calculator, and it kept popping up as the first one whenever I type it into Google. So now I just use Lentech. So what Lentech is you type in the formula as shown. So our formula was NH2 in parentheses 2 CO. So we're going to type that in here. If I could get the right home keys. Hold on. There we go. And when I hit enter, boop. What it does is it adds up all the molar masses or atomic masses on the periodic table for me. So each nitrogen is 14.01, each H is 1.01, each C is 12.01, and each O is 16. And then it multiplies them by the number that they have, so I get these, and then it adds them all together and goes to the hundredths place. And so we're all done, and you get the answer that is shown on the screen here. So it's basically the calculator online will do it for you. Now, Lentech does have some significant figures issues in the sense that hydrogen is pretty heavily rounded here. So for hydrogen, we only get 3 sig figs, but we're only doing addition, so who cares, right? As long as your molar mass goes to the 100ths place, your result will be fine when using Lentech. If you are just working with hydrogen by itself for something with a tiny molar mass less than 10, so like H2, don't do H2 on Lentech because you will only have 3 sig figs. Try to have at least 4. But for virtually everything you're going to use on Lentech, it's going to spit out at least 4 sig figs or more. And just use all the numbers that you get, and you'll be fine. Use all the decimal places that are shown. And that's how you do molar masses. So we can do this for any compound that I can think of. So here's a bunch of them. Really, this is just an exercise of go type it into Lentech. If you want to do it by calculator or by hand, you totally can. So I'm going to let you do that. I'm going to give you 4 or 5 minutes to play around with Lentech, just to get familiar with it. It's the second link right here. And I will punch in the results that I got on screen for you in about 5 minutes. So see you in a bit. All right, one more minute to play around with Lentech, and I'll go over the answers. Whoops, that's in the same window, so you can see. Hey, look how many people are here right now. So. All right, so I'm just going to type these in here. So let's do aluminum chloride. So I got 133.34 for that. I'm not going to write it down. You can just see it on the screen. For barium hydroxide here, make sure you put parentheses around it, around the OH. You should get 171.34. And then ammonium phosphate, I get 149.09. And then finally P4010, 283.89. That's just a how-to on Lentech. It's pretty straightforward, but that is a website that is worth bookmarking because it will save you a ton of time calculating formula masses for everything, because we're going to use this so many times for the rest of the quarter here. Now, a feature on Lentech is percent composition. If we go back to Lentech real quick, we can see that on the screen it shows us what the percent by mass is in this column right here. So for P4010, by mass, phosphorus was 43.64%, and oxygen was 56.36%. The way that you obtain those percentages is by using the percent by mass formula. For any compound, the percent of X in that compound is expressed in the following way. Whatever the mass of X is that you're looking at, so you look it up on the periodic table, divided by the total compound's mass. Now, it's important to note that this includes all of the X in the compound. So don't just say, oh, well, X is oxygen, so I'm going to put 16. If you have 4 oxygens, you do need to multiply that by 4 because those 4 oxygens are part of the mass. So include all the oxygen in your compound if you're doing percent O, include all the hydrogen in your compound if you're doing percent H, and so on and so forth. Once you know this ratio, you multiply by 100% to get the percentage of your element in that compound. So as an example, what percentage of water is oxygen? So we can calculate that. And of course, I'm going to do the calculation at least once before we go to Lentech and just have it do it. Because this is, again, this is a pretty trivial calculation. So the percent of oxygen, oops, my pen fell off the screen there, is the mass of oxygen divided by the mass of water. And for oxygen, that is, according to the periodic table, 15.999, so I'm just going to write 16.00. Divided by the mass of water. And I could type that into Lentech. I just happen to have it memorized, so I'm not gonna spend time doing that. These units cancel out. Times 100%. And I get 88.6 0.79% oxygen. Now, let's suppose I ask you to determine the mass percentage of all the elements in water. So the other element is hydrogen. And I could totally do mass of H divided by H2O. Or I could just say, well, there's 100% in the whole thing minus the percentage of oxygen. Which would just be this. And there you go. So there's oxygen up there, and then there's percent hydrogen. Provided I did my math right. 88 and 11 is 99. Yeah, that's fine. Okay. But again, that's tedious, right? So if I click on... Oh, I gotta go back over here to do it, because that's where I've captured it. If I go back to here, and I just type in H2O, it does it for you. Look at that. So remember, work smarter, not harder. Use the resources you have at your disposal. All right, I did some rounding there, it looks like. That's fine. All right, so figuring out the mass percent composition of aspirin becomes really trivial. We could just type it into Lentech. So here we are. Aspirin is C9H8O4. So there's my mass percentage. 60% carbon, 4.48% hydrogen, 35.52% oxygen. Yeah, no big deal, right? We can do that no problem using Lentech. Now, once we have these mass percentages, we can start doing other things with them. For instance, what if I had to work backward? I'm going to give you the chemical formula, or I'm going to give you the mass percentage of ibuprofen and its formula mass. Now, notice that I cannot go backward on Lentech, so this is only good if you know the formula. If you don't know the formula, then something you can do is you can just try looking it up in here. Maybe it's in here. And what are we looking for? Ibuprofen? Yeah, it's not in here, unfortunately. If I gave you acetaminophen, oh, it's not in here either. So these are just common amino acids and organic compounds. But if you don't see it in there, it's time to bust out the pencil. Or pen, or whatever it is that you're using. And so that's where the power of the formula really shines through. So let's put this on the screen. So we need to figure out this formula. And the way that we're going to do this is we're going to manipulate the mass percentage formula. Now, looking at this, I know what the mass percentage of, say, carbon is. So if I do mass percent carbon, I know that this number is 75.69%. Because it says that on the problem statement right there. Now, what's the total mass? Well, I know that too. A 100% is just a number. All I don't know about this is how much carbon is in there. But what I do know is that the mass of carbon equals however many carbon atoms there are times 12.011 AMU. So if I substitute this and then just solve for X, I'll know how many carbons are in the formula, right? So let's do some algebra here. So I'm going to rearrange this so that I just get the mass of carbon by itself. So that means mass percent C times the total mass divided by 100%. That gets rid of these terms, equals just the mass of carbon, which is this, right? Where X is the number of carbons in our formula. Well, I'm just going to divide by 12.011. And we'll solve for X here. So this is going to be 75.69% over 100% times the total mass divided by carbon's mass. And when I do that, I get 12.99999, or in other words, 13. Because the number of atoms in the formula has to be a whole number, right? We can't get a fraction, so we're going to just round to the nearest integer. So that means that my formula has 13 carbons in it. And I can do the same thing for all of the other elements there. So we've got hydrogen and oxygen. So let's set up the same formula for hydrogen. That would be mass percent H equals mass of H, which in and of itself equals X times whatever H is on the periodic table, divided by the mass total times 100%. And I've given you all of the numbers to fill in the blanks. So you know what this is, and you know what this is. So solve for X. So I'm going to have you do that, and I'm going to have you do that for oxygen. And what I want you to tell me is how many H's are there, and how many O's are there, and what's the formula. And once you've done that, we'll go over the answer together. Okay? So give this a try. We'll go over the answer in about 4 or 5 minutes. One more minute, we'll go over the answers. Type your formula in the chat once you got it. All right, let's go over the answer here. So for hydrogen, we're going to set up the problem just like we did for carbon up at the top there. So there's my algebra. I just rearranged it. The mass of H was, according to the problem statement, 8.790%. The total mass is the same as it was before. That's 206.29. And so that's going to tell me the number of hydrogens that are in here. And I get 17.99 hydrogens. That's close enough to 18. And I can do the same thing with oxygen. We'll do that up here. We'll just replace this with for oxygen. Oops. And so the mass percentage of oxygen is 15.51. The mass total is still 206.29. And when you do this process, you should get whole numbers. Here I got x equals 2. And so putting all this information together, my formula becomes C13H18O2. So it is possible to work backwards, but it is a lot more involved. All right. I have other problems for you to try. How much hydrogen is present in a 20-gram sample of acetone? Notice I didn't give you the mass percent, but you can go look it up on Lentech. Go ahead and try that. I'll give you 3 minutes to solve it. One more minute, we'll go over the answer. All right. So what mass of hydrogen is present in a 20-gram sample of acetone? Well, if you just go to Lentech and you find the percent mass, that's not Lentech, that's a different window. It's just blue. It's the same color as Lentech. It's just a thesaurus. All right, so we're going to type in acetone's formula in here. And so we would find, so the molar mass is 58.08, but we don't really need that. The mass percentage of hydrogen is 10.41. So what that means is that in any sample of acetone, 10.41% of that will be hydrogen. So we can do the calculation like this. 20 gram, crap. Try that again. 20 grams of acetone times 10.41% of that is acetone, which we can write in the following way. Right? Because what 10.41% means is that in 100 grams of this stuff, 10.41 grams of it is hydrogen. Those units cancel out. And we just punch in the calculator. 20 times 10.41%. And I get 2.08 grams of hydrogen. That shouldn't have this extra sig fig there because I only had 3 right here. So as you can see, there are all sorts of different applications that you can do with this. I have one more for you to try. I have a molecule with one carbon atom that is 74.8% carbon by mass. What is the formula mass of the entire molecule? Again, try writing down the formula for percent mass and solve for the missing part. And again, I'll give you 3 minutes to do this. Just some time to work on these problems. One more minute, we'll go over the answers, and then we'll take our break. All right, let's go over the answers. So again, if we write out the mass percent formula, that should be a T, but I wrote an X for some reason. My T fell on its side. There we go. I need to solve for this term down here, mass total, right? So I could rearrange this formula to become mass total equals mass of carbon divided by the mass percent of carbon times 100%. And my percentages would cancel out. And so that would be, there's one carbon atom, and each carbon atom weighs 12.01 AMU, divided by the total mass, oops, not the total mass, sorry, the mass percent of carbon, which was, 74.8%, times 100%. And when I do that, I get 16.06 AMU. Trying to cram that in there, unfortunately. Oh, and I only have 3 Sig Figs, so I should have 60.1. All right, so there are some examples on how to manipulate the mass percentage formula. I have more examples for you to try on the next slide here. We're going to take a break. I'll go over the answers to these after the break, so if you want to work on them during the break, that's totally fine. We'll start the timer, we'll get the music going again, and we'll see you in 10 minutes. Alright, we're back. Oh, I gotta get the music out of here. Hold on. Alright, so hopefully you had a second to look at these problems. Maybe even do one or two of them. I'll give you a few more minutes to work on them. The first one is literally type it in Lentech. The second one is and the second and third ones are similar to what we did before. We'll go over all the answers in like 3 or 4 minutes. Alright, let's go over the solutions here. For this first one, you got to know what ammonium phosphate is, so I hope you know your polyatomic ions and the naming rules. But in case you didn't, and that got you hung up, here's the formula for it: NH43PO4. And when I hit enter, there's the percent composition by mass: 28.18% nitrogen, 8.11% hydrogen, 20.78% phosphorus, and 42.93% oxygen. All right. Dietary recommendations suggest that adults limit their salt intake to no more than 6 grams per day. What mass of sodium is present in this quantity of sodium chloride? So, if you're only allowed to eat 6 grams of table salt per day, first we need to figure out what the mass percentage of sodium chloride is in table salt. And so that is, sodium is 39.34% of the mass of NaCl. So if we go over to this here. Sorry, just getting this set up here. And where'd my pen go? There it is. Okay. So I know that 39.34% sodium in table salt according to Lentech, if I'm allowed to have 6 grams of sodium chloride, I can write this as a percentage right here. And so I get, well, if I could type it in correctly in the calculator, 2.360 grams. Or you may have heard this number quoted somewhere, which really they just reported as 2,300 milligrams, which is close enough, right? All right, and then the last problem, if I have a molecule with 2 nitrogens in it, what is its formula mass if those nitrogens are 63.6% of the compound? So the mass percentage of nitrogen in this compound would be the mass of nitrogen over the total mass times 100%. Well, I need to solve for the total mass here, so I'm just going to rearrange the expression. And then we'll fill in the information. So I have 2 nitrogens, and each nitrogen is 14.01 AMU. It should be a 2. 2. There we go. The mass percentage of nitrogen is 63.6% times 100%. And I get 44.1 AMU. So, again, lots of different ways to use this formula. Make sure that you are up to scratch on how to manipulate it and use your algebra skills, because you can't always just type it into Lentech. All right. So that's an introduction to the types of calculations that we're going to be doing. This last slide in this section is just a suggested strategy for dealing with Sig Figs. As long as you have up to 2 decimal places, you will be okay, provided that your mass that you're looking at is greater than 10 AMU. If you're below 10 AMU, use 3 decimal places so that you have at least 4 Sig Figs in your answer. You want at least 4 Sig Figs, so that that is not the thing that limits your Sig Figs in your answer when you type it into Canvas. All right. So just make sure that you are reporting to at least 2 decimal places when you use the periodic table, using whatever periodic table you're using. There's tons of them out there, I realize. And you'll be in good shape. All right. Any questions, let me know. Y'all are very chatty today in the chat, I can tell. All right, the next chapter, or the next section of this chapter, is one of the most important concepts in this class. And so this is the introduction of a new unit called the mole. And the mole is a method of counting large numbers of teeny tiny things. It turns out that in a small quantity of matter that we can have, so like 10 or 12 grams of stuff, for example, for carbon specifically, in 12 grams, there are this many atoms in it. And we're going to use that quantity and call it a mole. Now, why 12 grams of carbon? we selected that as a reference and then determined the number of atoms that were in there experimentally. And the number that we got was 6.022 times 10 to the 23. We're going to define this number as 1 mole. Now, in the same manner that 1 dozen is 12 objects, or 1 couple is 2 objects, 1 mole is this many objects, 6.022 times 10 to the 23. So just think of it as a grouped sort of counting. You can count by dozens, right? I go and buy 5 dozen eggs. That would be 5 times 12 or 60 eggs. If I buy 5 moles of oxygen, that's 5 times 6.022 times 10 to the 23 atoms of oxygen. It's the same premise. It's just a group sort of counting. Now, this number specifically is referred to by the person who did the calculations to get to it. So we're going to call it Avogadro's number after him. So I'm going to refer to Avogadro's number all the time in this quarter. You're going to see this number so many times that you will memorize it pretty much instantly because it's so unique. Everybody knows Avogadro's number. And Avogadro's number is a humongous, humongous number. This is unfathomably large. For instance, if you were to take a piece of paper, like an 8.5 by 11 piece of paper, and stack another piece on top of it, somehow they stay standing, I don't know. You're going to make a tower out of these. So these are just 8.5 by 11 pieces of paper stretched end to end. You're going to make a tower that goes up into the atmosphere. How far will you get when you've placed Avogadro's number of these? Well, if you stacked a mole of 8.5 by 11 pieces of paper end to end, they would go so far that you would go past the moon. You would go past Mars, Jupiter, all the other planets. You'd go past every other star in the galaxy and all the way to the next galaxy. Which is real far away. You think interstellar travel is difficult. Try intergalactic travel. And yet our paper would reach that far. I've written textbooks here, but textbooks are the same. Same height, more or less, as a sheet of paper. And that's because this number is so humongous. Here's another example how big this number is. If I gave you this much money, you win the mole lottery, I give you a mole of dollars. How could you distribute that money to all your friends? Maybe you could have enough money that you could distribute it to everybody on Earth. Maybe you could do a lot of distributing money. Share the wealth, right? Take down the system. No more capitalism. Mole economy. If you got a mole of dollars, you would have enough money to share your winnings with every person on the planet at a rate of $3 million per second for every single person on the planet for the next 100 years. That's how big a mole is. Of course, if we did that, the economy would collapse because money would be worthless, and we would wonder why we had the mole lottery to begin with. But a mole is a huge number, and it's kind of impossible to fathom how big this number is. And the reason for that is because atoms are so tiny. And yet, having this huge number of atoms leads us to reasonable amounts that we can measure in our hand. So like 18 milliliters of water is a mole, it turns out. 12 grams of carbon is a mole. 55 grams of iron is a mole. How do I know these numbers? Well, I'm just getting off the periodic table because the periodic table tells you that. This is just a toothpaste for dinner comic that I thought was funny. I'd love to talk to you later, Avogadro. Can I get your number? You're gonna need a bigger piece of paper than that. All right, so let's do some calculations using the mole. How many atoms are in this sample of carbon? Oops, where is my sample of carbon? The mole is just dimensional analysis. If you remember all the way back in Unit 3, where I gave you all those problems that are like, convert feet to meters, or here's an orc on a motorcycle, how far does he ride if this is how much gas he gets? The reason for all of that stupid nonsense is because we want you to get familiar with dimensional analysis, because now you have to use it. I know that this relationship is true because we just defined it. So that means when I do my dimensional analysis, I can cancel out something down here by putting the same thing as up here, and then we'll put the other thing in this spot. And then we'll run the numbers. In a mole, there are Avogadro's number of atoms. And so I can get that quantity by punching this into the calculator. If my calculator would work. There we go. I read the numbers wrong. It's still an unbelievably large number. But that's where we're going with these types of calculations. All right, next question. An automobile airbag inflates by deploying this many molecules of nitrogen into the airbag. How many moles of nitrogen were put into the bag? So I want you to turn this quantity of atoms into moles. And we'll go over the answer in about 3 minutes. So give it a shot. Type your answer in the chat, just so I know someone's watching. One more minute, we'll go over the answers. All right. I replaced the carbons with nitrogens because regardless of what the atom is, the relationship is the same. And in fact, I just realized this should be N2, which makes these molecules. The relationship works out the same. So I have this many molecules of N2. I can do the dimensional analysis by setting up the units so that they cancel. There you go. Now we'll do the numbers. In 1 mole of nitrogen, we'll do that. There are Avogadro's number, 6.022 times 10 to the 23, molecules of it. And we punch it in the calculator. And you should get 2.74 moles of N2. So those are some very basic calculations between atoms and moles. Now, counting back and forth between atoms and moles, that's easy enough because we're only using one number. But we don't really measure anything in count. Like, I can't put a pile of molecules on the scale by scooping it out of a box or a bottle or whatever and then getting the number of molecules. We don't really do that. We measure mass, right? Mass is more relevant to us because it's easier to conceptualize. We know about what a gram is. We know about what a kilogram is. So we need to be working with mass. Oops, I have more examples for you to try here. In the next section, we will do that. I'll give you a second to try these problems. We'll go over the answers in just a little bit. We'll do 5 more minutes, and then we'll talk about mass, and then we'll kind of wrap things up here because we're getting towards the end. 1 or 2 more minutes, we'll go over the answer. All right, let's go over the answers here. Oops, that didn't capture correctly. All right, so again, we're still using the relationship 1 mole of whatever, so in this case it's lead, is Avogadro's number, atoms of lead. I have this many moles. So let's do the dimensional analysis. And then we'll run the numbers here. And so when I punch that into my calculator, I get 5.03 times 10 to the 23 atoms of lead. And then we can do the same thing with this nanoparticle, which is just super small. So it has a really tiny number of moles in it. But this problem is really just designed to get you used to... Oh, this is gold. This is just designed to get you used to working with these crazy magnitudes of powers of 10. All right, how many gold atoms are in here? Well, in 1 mole, there are still Avogadro's number. So this is exactly the same type of problem. When we punch it in the calculator, I get 3.22 times 10 to the 13. So even though it's a nanoparticle, it's super, super tiny, it still has trillions of atoms in it. Which is kind of ridiculous when you think of it that way. All right. In the next section, we're going to talk about the relationship between grams and moles off the periodic table, but I don't think I have enough time to complete it because there are just as many problems here. So I'm going to just introduce the concept real quick, and then we'll do the practice problems next time on Tuesday. So if I want to know the mass of 1 mole of an element, it turns out that on the periodic table, the atomic mass tells you that information. So for instance, if I look up carbon on the periodic table, 1 mole of carbon is just the number that is given as its mass number. 12.01 grams is 1 mole. For iron, 55.85 grams of iron is 1 mole. Why is it different? Well, every carbon atom has a certain number of protons and neutrons in it. Every iron atom has a certain number of protons and neutrons in it, but there's way more protons and neutrons in iron than there are in carbon. So if I have Avogadro's number of atoms, I'm going to have more mass as a result. And so these numbers that are shown on the periodic table come about from that. We've defined the AMU such that this relationship holds true. So I get all of these numbers from the periodic table. So if I want to do a conversion from moles to grams, I just find the atomic mass on the periodic table. And so that gives us another relationship we can do. We can turn moles into atoms, or we can turn moles into grams. But in order to turn moles into grams, I need to know what the element is that we're working with. So to leave you with one example, this is called the molar mass, by the way. So we can look up the molar mass of these elements. They're on the periodic table. That's not difficult to do. And you can do the same thing for compounds. So if I wanted to go to Lentech and type in the number for sodium chloride, it'll tell me that its mass in AMU is 58.44. We just change AMU to grams per mole. They're the same unit. So now you can do this with molecules too. And again, you can just type that into Lentech. You could type these into Lentech. No problem. We'll just do the first one for an example here. Because if we're going to be using these giant substances in calculations, you're not going to want to add 11 carbons and 22 hydrogens and 11 oxygens in there. So if we go to lactose here, C11H22O11, then its mass in grams per mole, and you can see that it's been using that unit the whole time, is 330.28 grams per mole. And you can do that for all these other substances too. That's not difficult to do. But when we return on Tuesday, we're going to start doing these relationships. We spent all day today, or all of the second hour, doing this relationship here. We're going to add in this relationship using these relationships between grams and moles that we just discussed. But I don't really feel like we should start a new topic with 5 minutes left and then not have you have a chance to do any problems here. Hooray, there are people that exist. It's not just me here. Alas, it is time to go. We're going to call it a night. I've just been alone too long. I can't bear it anymore. But also, probably what's happening is that everybody is taking the quiz, because there is a quiz due tonight and there's a quiz due tomorrow. So make sure you get those done. And make sure you tune in tomorrow, because we're going to be continuing Unit 12 and continuing our discussion of moles and calculations involving them. Take care, and I'll see you tomorrow.